All right, welcome to the Kepler Insider's view of the Kepler K2 program, the Insight to Innovation. Want to get started here with a little bit of history and what Kepler's about. Johannes Kepler, this is the part that everybody hates in history, right? The names and dates and all that kind of stuff. Johannes Kepler was a German astronomer in the 1600s. He actually started his career in the 1590s. He continued Tycho Brahe's work and developed two new laws of planetary motion at the time. They're still in effect today. And he stated that all planets revolve around the sun in an ellipse. And this is really important because it's important to the work that we've done on the Kepler program. Kepler wanted to answer some significant science questions. Are terrestrial planets common or rare in the galaxy? What if they are, whether they are common or rare, if we have them, what are their sizes? What are their distances from their stars? How often are they in the habitable zone, which is what we define as where liquid water can exist on the surface and pool in the valleys? And then what is their dependence on stellar properties? Our sun is pretty stable, doesn't have a whole lot going on. You know, we have flare activity, but really that's kind of benign in the universe as we're discovering. And other stars are far more active, and so we wanted to know, is there a dependence there on the stellar properties for where the habitable zone is. So let's give you a little bit of what Kepler's about. Spacecraft was developed by Ball Aerospace Technologies Corporation here in Boulder. They provide the mission operations manager, or MOM, and we do other programs with them like ISAT and QuickScat. What you see here is the photometer array, and it's kind of hard to see, but right there and on each one of these corners is a single pixel in there that helped us point Kepler very accurately, and it's called the fine guidance sensor. The actual results that you see here, this is one of the images that we had from one of our campaigns. Kind of shows you what a full frame image looks like. Kepler was not intended to be a full frame, an imaging satellite. It was strictly photometric, which is basically measuring the light intensity and especially the changes in the light intensity. But if you get enough of these full frame images, you can stitch them together and come up with some really neat stuff. I'd like to show you this video that kind of gives you a bit more of the history of the program. It explains it really well and a lot shorter than I can.
After getting my PhD, I became aware of this fellow at NASA Ames Research Center, Bill Barucki.
I would see him at all these meetings. They were very small meetings back in the day. And like he'd literally be by himself out having dinner, so we would join him and chat about things, and he was very persistent.
Bill walked around the halls, and whenever the Ames managers saw him coming, they turned and walked the other way.
Bill Barucki wrote a paper in the 1980s that described the transit method. When that planet passes in front of the starlight drops by a tiny, tiny amount. And by measuring the brightness of the star, minute by minute, we can detect planets going in front of the star, and we call that the transit method. And detectors that could measure that precise drop in brightness didn't exist yet.
To be successful, all one needed to do was build a photometer 1,000 times better than anyone ever built one. But I'd worked on the Apollo program, I'd worked on other programs, so that's not really that scary. You just need to get down to brass tacks and find out what's required and build it. There just is no way of finding small planets in orbits like that of the Earth unless you go into space. You must go into space.
He kept getting shot down by the review panels for various reasons, and each time he'd fix the reason and go back a second time, and they basically said it's not going to work. Well, Bill Barucki didn't bother reading that report, or at least did not take it to heart. He kept on his crusade to show that transit detection should work.
He was able to demonstrate in the lab that he could measure the precision required to find Earth-sized planets orbiting sun-like stars.
Some people call it stubbornness, but the point is I knew it would work.
So he proposed and reproposed, and eventually he conceived of a Discovery-class mission that was later called Kepler.
It was 25 years between the date of publication and the date that Kepler actually launched.
1-0 and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Kepler just delivered so much tremendously new things we never even conceived of. And the things that were on our wish list, Kepler found for us.
This data was being displayed for the first time on the computer monitors. And there was the transit of that Jupiter-sized planet, and the data was like beads on a string.
Kepler has transformed our understanding of exoplanets. What Kepler was designed to do specifically was to go after terrestrial or rocky planets that are in closer orbits to stars. We now know from the Kepler data that planets like the Earth are in fact common in the galaxy, and that's something we fundamentally didn't know before Kepler.
The first exoplanet was already diverse, and Kepler continued to find more and more planets that didn't fit the norm, both in size, in composition, in distance from their stars. So when you think about how many stars there are in our galaxy, there are a few hundred billion, and if each one has one or maybe more, we're looking at a few 100 billion planets.
To accomplish something great, you have to have persistence.
To succeed in exoplanets, we have to be very ambitious and very bold.
Kepler's impact was extreme, certainly more than I'd ever imagined. It's basically opened up an entire new era of astronomy.
New era of astronomy is an understatement. There's been a tremendous amount of papers done in Kepler's area, and it spawned new studies. Astroseismology, for example, is a whole new field. And the way it started out was just like this. Kepler points at a single region of the sky. It was launched in 2009, and the whole point was to measure the brightness of 100,000 stable stars in the field of view. We were going to stare at the same spot for years on end. We used a CCD that's not unlike the CCD in your camera or now your phones. You actually probably have more capability in your phone than Kepler did. But the CCD exposure integration was 2.5 to 8 seconds. And what we did is we would accumulate exposures in 30-minute long, what we called long cadences, and 1-minute short cadences. And we would collect that data and then clock it out every half hour. Typically, the collection was a half hour. The clocking in and actually writing it to the solid state recorder was another 10 or 15 minutes. But it did that day in, day out, all the time, except for when we were actually downlinking the data. The spacecraft itself has a high gain antenna. Here it's just a small 1 meter dish on with a transmitter capable of getting back to the Earth. And then of course we've got omni antennas on either side, so we could do X-band uplink and downlink in real time. It was what we call dual string electronics, which means there was redundancy if we had a failure. The fine guidance sensor, which I was pointing out earlier, is what really enabled us to get extremely accurate pointing. And this is functionally the equivalent of keeping an imaginary telescope in San Francisco pointed at a theater-sized movie screen in New York City. That's how accurate it was. The flight segment, what we call the flight segment, is really comprised of both the spacecraft and the photometer. The spacecraft provides all the standard stuff that spacecraft do. There's got to be an attitude control system, there's got to be electrical power system, there's a propulsion system, there's thermal system and structures, and with few exceptions, pretty much everything was redundant. So what you see here is just the spacecraft portion, and here's the photometer. For scale, you can just see a guy over here in a bunny suit, so that you can kind of see what's going on. So the photometer itself is a Schmidt telescope. The actual array that you saw earlier is right about here on the inside of that, and the light comes in, bounces off of the primary mirror, and hits that photometer right here. So here's a kind of a hardware placement overview to kind of orient you to what's going on with the spacecraft. Pretty much all of the electronics are mounted to the outside for thermal balance and conditioning. We've got a couple of star trackers pointing in 2 different directions so that we can track stars and know our attitude. We've got RCS thruster modules on each of the 4 sides here that allow us to control the attitude of Kepler. Let's see, move on. Orbit design. The original orbit design was intended to just get us to this point right here. Must be less, the telecom must be less than half an astronomical unit, which is the distance from the sun to the Earth is what we call an astronomical unit. Had to be less than half of that distance after the 4-year primary mission. It also had to have thermal stabilization because we're using a photometer. It's very sensitive to heat, but it wasn't critical. So basically, the thermal considerations and the design was based upon being at just about 1 AU at its longest length. This would be the original mission plus the extended mission under the original concept. And then, really, why did we need this orbit? Why are we in an Earth trailing orbit around the sun? Well, the primary purpose of that is to ensure the stability of the spacecraft. There's a lot of effects from orbiting the Earth, not to mention a lot of debris and other kinds of things. And so we wanted to get it out away from the Earth so that we didn't have the gravitational effects from the Earth's oblateness, or not quite being round, and so it was mainly a stability thing. And then the power was basically going to be limited by the fact that the battery was only sized. We're always going to have the solar rays facing towards the sun. There is no eclipse, no opportunity for eclipse, and so battery didn't need to be that big. It just needed to be able to regulate the bus. So, ground system roles and responsibilities. I won't take the time to read this to you, but just suffice it to say, Ball was the spacecraft experts. They provided us with an awful lot of engineering support. They held on to configuration management for a lot of things, and then granted us the ability to do that as we moved into the program. And so we actually got a chance to move some of these things on the left side over onto the right side. The Laboratory for Atmospheric and Space Physics handled the real-time flight operations. We use professionals like myself in the flight controller and flight director position, and then we use students here at CU in the command controller position. One of the things that's really cool about this location is it's the only place in the country, I dare say the world, where you can get this kind of experience as an undergraduate student and actually command hundreds of millions of dollars worth of spacecraft, and not just one, but 4 or 5 or 6 of them. The Kepler ground segment was, this is very simplified. Basically, the Flight Planning Center, or this is Ball Aerospace, provided us with all of the necessary products. They had the satellite test bed, which is basically our simulator, and they provided us with all of the engineering groundwork for what they wanted to do on orbit, and then we would find a way to operationalize that. And I see one of my lines didn't get moved. This, which should be over here. And we would operationalize it, which means that we would take it and put it into a form that was suitable for uplink to the spacecraft. Most of the time that was taking an ASCII file, a text file, converting it to a binary and preparing it for an upload, and then setting up the scripts necessary to do those uploads. And we would use the Deep Space Network, which is our ground antennas, to radiate all of those commands up to the spacecraft. We'll take down telemetry from the spacecraft and feed it back to the Flight Planning Center and to other agencies as well. On the left side here, you can kind of see one of our custom pieces of software that we developed. This is what we call the Mach clock. The Mach clock is custom designed to give us the actual events that are currently planned in our planning system, as well as what's going on with the DSN network at any given time. And so we can see the next, what's going to happen next and when it's supposed to happen. Some of the things that you see here, this is just from this past October. You can see here that where we had what we call resaturations and data collection times interleaved in that process. And so really good piece of custom software. Guess what? Made by students and professionals working here. The DSN, I just think this is kind of a cool picture, so I include it. The DSN is a shared network. They service a lot of different programs. And each one of the programs has its own program identifier. Kepler's was KEPL. And I apologize for the size of it, but the functional part of it is that this is showing you from the Earth the right ascension of each one of these spacecraft. And you can kind of see that there are certain directions that are really popular and some directions that are not. Kepler is right here, and so when we're in this kind of situation here, we're not competing with a whole lot of people. But when we're over here, we are competing with a lot of people, and a lot depends upon what time of year we're looking for those contacts and whether we can get the antenna arrays. And we have to do a deconfliction process in order to do that, and that's part of the planning system, and it's part of the back and forth that we do here at LASP, and gives you a little bit of insight of some of the challenges that we have on it. The view periods for each one of the sites at the DSN is labeled here. This is basically February, May, August, and October. And so this kind of shows you the seasonality. If we just pick out one, say the blue one, which is Canberra. There it's cyan, Canberra, cyan, okay. You can see it's pretty low elevation during the summer months because it's in the southern hemisphere during our summer months. And it gets even worse that's midwinter. It gets even worse in our summer months, but then it gets really good towards the end of our summer and the beginning of their summer. And it's outstanding in their summer. So that just gives you a little bit of difference. Why does that make any difference at all? Well, the elevation actually has an impact on how much data we can get down and how fast we can get it down. So this is the locations of the Kepler planet candidates as of December 2011. And I know some of you are thinking, Lee, it's 2018. Dude, come on. What have you guys discovered for us lately? Well, this was a really cool picture, but what's really key about this is this was the image that we stared at for just over 4 years. Okay, and these are all the different kinds of planet candidates that we got. The blue spheres are Earth size. The super Earth size are green. The Neptune size are orange, and the giant planet sizes are red. And the one thing you can really get from this is the Earth is kind of unique in the sense that it's smaller than the average that's out there, right? The typical planet that's out there is about 1.5 times the size of Earth or larger. So it's a small world. Science is about knowing. Engineering is about doing. I like to say that engineering is really just making stuff up and figuring out how to make it work. So for our operations, we have to deal with various things. We have to deal with anomalies. We have to deal with new ideas that people come up with. And they can come from virtually anywhere. It could be from a discussion that we're having with Ball. It could be a discussion that I've had with students. Some things just came out of the course of a discussion, and we ended up developing a whole program to do various things. What you're seeing here is 2 full-frame images. This was at the start of Campaign 10. We had already lost modules 3 and 7 earlier in the original mission. And during Campaign 10, sometime during Campaign 10, we lost Module 4. And that, of course, presents us with an anomaly that interrupts the science collection. So we have to turn the spacecraft, download the data, figure out what went wrong, recover the spacecraft, and do the various things necessary to restart. Because it's not just like getting in your car, starting it up, pulling out of the parking space, and going. You have to do a whole lot of planning to get into back into science from where you're at, because everything is situationally dependent. In 2012, Kepler experienced a reaction wheel failure. Wheel 2 was discovered at 0 RPM. We had some slight ability to get out of 0 RPM, which is to say we commanded it to rotate, and it rotated some, but it required more torque than we were expecting. And frankly, it looked like it was done. In that process, we developed some new analysis techniques. Some of our students actually wrote papers on that stuff and presented them at the Space Ops Conference this past April or May in France. They actually went to France. I wanted to go to France. I didn't get to go. But that was 2012. Kepler had 4 reaction wheels on it. That's kind of typical. It's called 3-for-4 redundancy. And basically what that means is that you can lose one and still have control of all 3 axes. So we replanned everything to deal with just 3 wheels, and we continued our operations. We figured out how to use thruster controlled safe mode, for example, which is something that we'd never done before, because we'd always gone to safe mode on wheels. And safe mode, for those that are unfamiliar, safe mode is just a way for the spacecraft to respond to an anomaly that'll put it into a safe configuration so that we can get to it later and make sure that everything's good, figure out what went wrong, fix the problem if we can, and then get it back into science. So we resumed science operations on just 3 wheels, and then in December of that year, we started to see, with our new analysis tools that our students helped develop, we started to see persistent elevated friction in reaction wheel 4. We modified safe mode for that thruster controlled safe mode, and we made plans on how we would recover Kepler if that wheel had problems. And sure enough, it did. In March 2013, the spacecraft was found in safe mode. By that time, we had thruster control safe mode on board and ready to function. And wheel 4 did not recover. As it turned out, it was seized up really good, and there was just nothing to do it. So we innovated some ideas and said, well, maybe we can, we can't hold standby, which is basically pointing at the galactic north and holding that position with the solar rays pointed towards the sun. So we said, why don't we, do something with, standby. We only have 2 wheels. We really can't do a whole lot with it. Why don't we do something with thrusters and use the sun's solar pressure as it pushes the spacecraft over? We'll fire some thrusters, really, really small thruster firings, and we'll push it back up. And then we'll do this nodding or bobbing in a box, and that way we can use very, very little fuel, and we can keep it in standby mode while we figure out what we're going to do next, because we really don't know. So at this point, this is where everybody in the world started hooting and hollering from the rooftops, Kepler is dead. There is no more data from Kepler. But the brilliant folks over at Ball had an idea. And we discussed it and thought, you know what, this could really work out. The spacecraft has a large offset from the center of mass. Remember, I showed you where the thrusters were nearly the bottom of the spacecraft. And so that means that everything, the hinge moment is just like this, right? And so we thought, well, we used the solar pressure on the point rest state. Can we use that to take science? And during one of our discussions with Ball, we tossed out there, we said, hey, why don't we just reverse the way we've been using wheels? Up until that point, we had been letting the wheels gather momentum and then desaturating them by using thrust to spin them down. We said, why don't we just reverse that and spin them up, make the body really, really rigid, and then we'll be able to control at least 2 axes. We won't be able to control the third, but maybe we can find a way to stabilize it. And so we tried it. We said, okay, let's give that a go. And so this kind of shows you reaction wheel 3 here on top, reaction wheel 4 on the bottom, and you can kind of see that they are mounted in different orientations so that they can have impact on more than one axis at a time. So that's and then 1 and 2 are just like it on the other side of the spacecraft. So the operations concept was, originally we're going to point at a specific region of the sky, but wait a second, we can't actually control where the solar arrays are, that way. We can't point at the same place. And so the idea was conjured up, maybe we can point in a different location. And so we started looking at the ecliptic as a possibility. And this actually kind of solved a couple of problems for us. It allowed us to balance the spacecraft, and it also allowed us not to have to deal with certain kinds of torques from pointing at the ecliptic north or south. And so we used the 2 wheels to gather the system momentum to actually spin the wheels up, and the thrusters to adjust attitude every so often. We could balance it very much like balancing a pencil on its end. It'll stay as long as you don't disturb it, right? But it's very difficult to keep it that way. And so the thought process was, well, if we balance it and then 6 hours later we tweak it with thrusters using really, really, really small thruster firings, hey, that'll work. So we tried it. So the thought process was we're going to divide the contacts between two different types. So we're going to be doing Ka band science contacts, which occurs about every 84 days. We actually take the spacecraft, point it towards the high gain antenna, towards the Earth, downlink the data, and then and that lasts about 48 to 72 hours. Because of the data rates. And then health and safety contacts and also science operations would happen 90 degrees off of that, and with the antennas pointed not at the Earth at all, 90 degrees away, it was almost like saying we're not going to be able to hear anything. But sure enough, it turned out that we could, and so we used the 70-meter stations along with, and we actually pioneered the 70-meter, 34-meter arrays that allowed us to get enough of a signal to be able to downlink data rates even during science operations. And so we would take that data, and it was at, this says 20 to 40 bits per second. We actually got down to 10 bits per second. Now, for folks over here that are old enough to remember dial-up modems, and I remember dial-up modems at 300 baud, and that's 1,000 times more or faster than this was. So we were communicating with very, very, very slow data. We used a 4-position team, which consisted of a mission planner who did all of the planning stuff behind the scenes, the command controller, which is our students, the flight controller, which is also some of our professionals and who also double as mission planner and other things, and then the flight directors, which we had 2 on each time. And each one of these people had a role to play, and in some cases we actually intermingled and changed roles depending upon who was on vacation and that kind of stuff. So we had a lot of capability built into our folks here. The 2 biggest impacts were the growing distance, because of it means a longer one-way light time, takes a lot longer to get the command in, but it also means a lower data rate. The further away you get from a signal, the weaker it gets, right? And so that's the thought process that goes on there. So one of the things we had to kind of figure out was how are we going to manage these campaigns? What are we going to do? How are we going to get the data off the vehicle is one question, and there was a whole part of the flight segment that we wanted to understand for the engineering on the spacecraft itself. But we had to figure out how we were going to manage the planning system here, how we were going to pull together all of the different resources, get them into a kind of recurring cadence that allowed us to do this work. And so one of our flight controllers, who has since gone on to bigger and better things, developed this really simple diagram of what we were really going to do. So basically we have different campaigns. We'll just call this campaign N, which is the first campaign, and we'll get the data loaded onto the vehicle. This is all the science target tables and housekeeping data and so forth. A lot of different commands that we have to do. We'll put it into Science Attitude, and we'll sit there for the first 7 days to check it out, make sure that it's going to work correctly, make sure that we've got the right thermal balancing, and ensure that we've got the pointing correct, because it's very difficult. You're going to use fuel every time you have to go back up and point the spacecraft at the Earth. And so if all of that's good, then we'll actually begin the science observation period. The science observation period lasts for somewhere between 75 and 84 days, and then we turn the spacecraft, point at the Earth, and downlink the data. And during that time, we're also commanding new target tables. We're setting up for the next campaign, and then not all campaigns overlap exactly, and so there might be some idle time. There might not be. Just kind of depends, and then we just kind of repeat. And so in that way, we found the path necessary in order to do the things that we needed to do for Kepler. A lot of that involved testing. It took us almost a year to complete it because we had to test various subsystems and ideas that we were working with and make sure everything was going to work. And then we took our first campaign. We called it Campaign 0. And the whole point of that campaign was to make sure that the science we collected was going to be useful, that the pointing accuracy was accurate enough, and that it was actually going to be useful. And boy, was it ever. Some of our students also worked hard on Systems Toolkit made by AGI to develop look angles and accesses for our Kepler model inside of STK. And one of the products that they came up with is this report here. STK, for anybody that's kind of familiar with it, is really powerful, but the display capabilities suck. And so they developed the necessary scripts and tools to produce this kind of output and give us a clear understanding of where the bright stars are going to be and whether that's going to cause, and other planets, and whether that's going to cause a problem for our satellite, for our star trackers, because our star trackers were really so sensitive that they would see a planet, think it was a star, and go, sending us off into Neverland and making us use fuel, and we didn't want to do that. So here's what the new program looked like. I wish I could claim credit for this graphic. This graphic actually appeared in Popular Science and in space at space.com, and it was a graphic to kind of explain pretty much everything about how the campaign system would work. We would point in one direction, and we'd start at minus 53 degrees angle to the sun, to the solar array. And as time went on, the spacecraft would move relevant to the sun, and you can kind of see the angles changing here. And right about plus 29 degrees is where we would have to terminate the campaign. We could no longer look in this direction because we didn't want sunlight going down the telescope. And so we would turn the spacecraft, make it point towards the Earth, downlink the data, and then point it in a new direction, and for another 84 days. And then we'd point it in a new direction for another 84 days, and that ended up being about 4 or 5 campaigns a year. So we still called them quarterlies. The whole idea behind the reaction wheels is we were going to balance the solar pressure right along this ridge line. And you can kind of see in the graphic here, when it's offset, there's a tendency for it to want to go one way. If it's offset the other way, there's a tendency to want it to go the other way. And so if you perfectly balance it, you get a pretty stable pointing. And in fact, it ended up only being an order of magnitude worse than the original mission, which was still very good pointing and better than any star tracker can do. And we got really excellent science out of it. So for 4 years, we pointed only at the Cygnus constellation, and we got lots of great science out of that. Kepler was always a statistical mission. And so the first things we found were the hot Jupiters, the planets that were larger than our own Jupiter, that were inside the orbit, effectively inside the orbit of Venus. Can you imagine a planet that big being that close to our sun? It would blot it out every day, right? And so, but it was a statistical mission, which meant we had to actually kind of watch for a very long time to see planets further and further away from their stars. Once we lost the reaction wheels, we had to look in new directions, and so we decided to look along the ecliptic. And so each one of these represents a campaign field of view around the ecliptic. And some of them actually overlapped. We actually managed to overlap some of our campaigns. We were on there so long. And so we started studying stars. And in that process, during that first 4 years, we figured out how to measure a transit and know that it was a planet in just one observation. Right? When we first started it, we figured we needed at least 3 and probably 6 or 7 before we could even call it a candidate. right? Now, with the refinements in technology and the software tools and stuff that we've developed, we can tell in one transit, which meant that we could actually tell a whole lot of planets in these areas. And then, when we overlapped some of these areas, we were able to confirm the longer period planets. And so, statistically, now that we have enough data, we actually start to see this right here. There's actually two different sizes of planets. There's the more common, like Kepler 452 Bravo, which is about 1.5 times the size of Earth. And then there's the more common Kepler 22b, which is somewhere in the 2.5 to 3 times the size of Earth. And Earth is over here, and it's not very common at all. So this is what's called an orrery. It's a fancy term, but basically it means it is a means of showing you the orbits relative to the star. And what I'm going to show you here, and it's going to kind of run, it'll run for about a minute, but I want you to pay attention to, let's see, I want you to pay attention to things like this and stars like this. Some of these stars are not at the center of their solar system. They actually revolve around their planets. Okay, so watch this. This is our solar system, our planets in these dotted rings. And this is just the first, or just 3 years of Kepler data, 3 or 4 years of Kepler data. See, watch these guys right in here. See this guy right here? That little one? That's the star. And you can see the temperature. Some of these are hot as lava. Some of them are blue like Earth. It's an enormous amount of time that we've and work that we've put into to get into these things. So what are the statistics? Well, here's what we know today, right? It's not just 2011 data. This is today's data. This was just released by NASA. We spent 9.6 years in space. We've got over 530,000 stars observed, over 2,600 planets confirmed, 61 supernova documented, including one we watched happen as it occurred. Right? We've never, when the supernova happens and you're watching that on the telescope, you have to deal with day and night, and you can only look and see, is it there, is it not there? And most of the time, we've never captured one that happened as it occurred, and Kepler got that data. 678 gigabytes of science data collected, 2 separate missions, almost 3,000, soon to be 3,000 papers published. We're 94 million miles away. A lot of commands, a lot of work by a lot of people. Many people cut their teeth, so to speak, on the Kepler program and have gone on to do other things. The reach of CU into other aspects of the aerospace industry is very deep, and it's all over the country. And here's my favorite part, 3.2 gallons of fuel. And if you want to do the math, because I know we all do, that's 30 million miles to the gallon. You know, one of the cool things about Kepler is, and especially the K2 program, is it enabled us to think outside of the box and wonder, you know, we're going to point in this one direction, and it's always going to be kind of the same direction. In fact, the way I showed it to you, we were always pointed away from the Earth, right? Whenever we were taking a campaign. And one of us were sitting around one day and went, well, what happens if we point the other way? Can we do that? Sure, why not? Let's see if it'll work. And so we did. And we actually took what we call forward-facing campaigns. And this is actually campaign 16, Fieldofview campaign 16. And you can see here November 25th, December something or another, December 6th and December 12th. And Kepler was on this piece of silicon right here when we took a picture of the Earth. But what were we looking at? One of our science folks is kind of an amateur cartoonist, and she drew this. She got talking to the other scientists, and she drew this, and they became wildly popular with the public. And I'm sorry that she didn't draw one for every campaign. She only started doing it the last year or so. And so we were looking at campaign Fieldofview 16. We were looking at the Cancer, the crab area, and the beehive cluster. And, you know, of course, they're not happy about that. We've got pulsating, rotating, and exotic stars. We were looking at asteroids. We were actually pointed in the same direction as those telescopes. And so guess what? This is the one where we caught the supernova. This one and campaign 17. I think it's campaign 17 that caught one of the supernovas. And this one is the one where we actually saw the Earth as well. At that time, Kepler was 9 light minutes away from the Earth, which is further than it is to the Sun. And of course, it wouldn't be a NASA diagram unless there was some kind of disclaimer that nothing is to scale. So we called it Wave at Kepler. We publicized it. I hope you heard about it. I hope you got outside and actually got a chance to wave, because this is you. And I remembered Carl Sagan when Voyager took its picture of Earth, having a speech in which he said, "We succeeded in taking that picture from deep space." And if you look at it, you see a dot. That's here. That's home. That's us. On it, everyone you ever heard of, every human being who ever lived out their lives. The aggregate of all joys and sufferings, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilizations, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived right there on a mote of dust suspended in a sunbeam. So what's next? You know, Kepler wasn't the first Discovery class mission, but it was the first looking for planets around distant stars. Bill Barucki had to propose it 5 times before he finally got NASA to fund it and say, yeah, we're going to go ahead and do it. You know, everybody was excited about Hubble. It got on orbit and it needed glasses. Spitzer turned out to be wonderful, but it wasn't looking at the transit method. It wasn't doing that kind of science. And so when Kepler launched in 2009, we had some confirmations from ground observations about planets already using the transit method, because the word was getting out. Transit method might actually work. And then when Kepler come online, we saw a lot of planets, far more than we ever imagined. We really didn't know how many planets were out there. We supposed based upon our sample of 1, or actually 9, planets, that other stars must have planets, but we had no idea whether it was common or rare. We really didn't know about any other star but our solar system when it came. And now we know hundreds of billions of stars in the galaxy, and nearly all of them have at least one planet. And 20 to 25% of them are in the habitable zone. TESS, the transiting exoplanet, the Explorer, is going to carry on what Kepler pioneered. And we actually got concurrent observations of the same things with TESS, which was a nice kind of passing of the baton. It launched in April 2018, the James Webb Space Telescope in March 2021, and WFIRST in the mid-2020s. That's where we're going next. So let me leave you with this thought. In the early 1600s, Johannes Kepler finished Tycho Brahe's work, which included the first 2 laws of planetary motion. In 1840, the French mathematician Urbain Le Verrier, not sure I'm pronouncing it correctly, any French people? Okay. He hypothesized the peculiarities of Mercury's orbit that did not match the laws of motion that Sir Isaac Newton put forth, might be the result of another planet in our solar system, a planet that he named Vulcan. And so from that time until the 1920s, the search for Vulcan was on. That's a long time. Nobody had observed such a planet, but the laws of motion said something was perturbing Mercury's orbit, and that search continued until Albert Einstein formed his general theory of relativity and explained the perturbations as a result of the space-time continuum, and that corrected all the flaws in our predictions. In the 1980s, we still didn't know if any of these planets existed outside our own solar system. And now today, we have that certainty of what's out there. Just imagine what we will know tomorrow, or next year, or 10 years from now. I want to take a moment to have you kind of look around. Everybody who's actually worked on the Kepler program, please raise your hand and show folks, yo, don't be bashful, raise it up. Come on. Okay. Any questions? Yes, sir.
How long do they expect it to continue to operate?
Kepler? So Kepler ran out of fuel, sadly, and that was announced a week or so ago. And we are in the process of decommissioning it. We'll send the commands soon, and we don't know exactly how long it's going to take us, but we expect that it'll be shut down. It's in a perfectly safe orbit. The orbit design is such that it will never get within 1 million miles of Earth. So basically, we're going to turn off the fault management system and turn off the transmitters, and it'll continue to orbit the sun forever. Other questions? Yes, sir.
What happened to the students' jobs who will control the Kepler? Do they continue to work on data, or?
Yeah, that's an outstanding question. The students are trained. They are actual employees of LASP. We hire them in the spring. We train them over the summer in 4, 5, 6 different satellite programs of which Kepler was one. At the end of that time period, we put them through a certification process that includes both written and practical tests, and then they begin doing their command controller work. While they're going to school, during the school year, they work 20 hours a week. During the summer, they work 20 hours a week. During the summer, they work 40 hours a week. And they do things like command the vehicles, they do analyses, they do engineering, development work, and a whole bunch of other things. Software development, they develop their own tools, and so forth. And so what happens is, when something like this goes on, and this is really kind of common in the aerospace engineering era, is we allow them to do other stuff all the way through, and so they just devote their energies to other programs. And then as we take on new programs, we train them up, and they assume those roles and positions. But there's always more work than there is time for. So, thank you. Yes, sir.
What majors are you looking for when you see applications for young people in these programs?
That's an outstanding question too. We tend to get people from the aerospace and physics majors, but we'll take anybody at any major if they are willing to work hard, they have a passion for space, and they are dedicated to learning, right? Because we'll train you on everything that you need to know. So we occasionally get music majors. I don't think I've ever seen a philosophy major, but if you have the technical aptitude for it, if you're a geek at home and a philosophy major here, then cool. One of the things about that is that we like people who are willing to step up and say, I don't know the answer, right? We want folks that are willing to work hard and do the job. And it's not that kind of work is not for everybody. Maybe for folks that don't like math, it might prove challenging. But on the other hand, we've got folks that have done it quite successfully too. So we consider everyone who applies. Other questions? Yes, sir.
Yeah. What's the relationship with LASP and tests? Is LASP doing anything with the test program?
Sadly, no. We actually applied to be part of that, and others were selected. So.
How about Ball? Same thing?
I don't know. I don't know that off the top of my head. Other questions? Yes, ma'am.
How long will it take to analyze all the data from the Kepler mission?
Wow, that's a great question. So here's the thing. We're no longer taking new data, but we've got a ton of data that still needs analysis. And that'll be years. There's money for the science office to continue analyzing the data. But here's the cool thing. You can do this as citizen scientists too. If you are interested in doing this kind of stuff, there are tools on the NASA Kepler website and the science office. One of the tools is called Light Curve, and you can go start combing through the data and looking for planets on your own.
I think I'll jump in real quick. We'll see that's the end of the regular program, but we will be up here for a bit. I'll be around. I can answer questions, but we'll let you head out if you need to go.
Thank you.